Thank you so much for the introduction, Damir, and for the invitation. And thanks all for coming and hosting this great colloquium. I also wanted to say, especially, it has become quite difficult for me to travel, and so I really appreciate venues that are continuing to have online options. So I thought I would start out with that. So yeah, what I wanted to tell you about today is some work that actually I started in grad school and actually talked to Damir about, I think, once at the time, and then kind of got shelved for a while. And then a couple years ago, a famous complexity theorist, Alan Selman, passed away, and they were having a memorial commemorative volume for him. And I was speaking with my advisor, and he said, "Oh, you should dust off that stuff about polynomial-time axioms of choice. Selman would have loved that." And so I dusted it off and realized now, 10 years later, I could prove more things than I could when I was in grad school. And so I turned that into a paper, and it turned out to have actually many more connections with Selman's work than even I originally anticipated. So this is in memory of him. Okay, and with that, let's get started here. So the main player here is the axiom of choice, and just to put everyone on the same page here. Oh, and I should say, please do stop me if you have questions. I appreciate the online option, but I also recognize people have limited attention spans online, perhaps more so than in person. So I've timed it for about 40 minutes. So there should also be plenty of time for questions. So please do stop me if you have questions. And Damir graciously said he would monitor the chat, so you can type them in chat or raise hand and interrupt and ask. Okay, so the version of the axiom of choice that we'll start with is this one here. So if you have a set of non-empty sets, S sub I, for some index set I, then there's a choice function which takes an index and spits out something in the corresponding set. So if you think of your sets as these urns here, the choice function chooses a ball from each urn. Okay. And classically, say in Zermelo-Frankel set theory, this is equivalent to many, many different things. I mean, there are literally whole books about things that are equivalent to the axiom of choice. So some of them you may have heard of: the well-ordering principle, Zorn's lemma, every vector space has a basis, and so on. But sort of intentionally, these statements all feel very different. And there's a nice quote I like. The axiom of choice is obviously true. The well-ordering principle is obviously false. And who can tell about Zorn's lemma, right? And yet, of course, in classical set theory, these are all equivalent. And so that leads us to study these perhaps from a more constructive point of view of, can we tell these things that sort of on the surface feel different? Are they actually different in some setting, some more constructive setting? And so the constructive setting that we'll be focusing on today is effective complexity, so polynomial time. And this is an informal definition because I don't actually know how to make this precise. But let's say a polynomial time axiom of choice is some statement where if you removed all the words polynomial time, polynomially bounded, and so on, you get some statement that is equivalent to the usual axiom of choice in ZF set theory. Okay. All right, so in order to make some of these statements, I just want to make sure we're all on the same page here and review some notation and complexity stuff. So sigma for us will be a finite set that is our alphabet. It will almost always have size at least 2. I forgot to mention that on the slide. So not a unary alphabet, but otherwise just some finite set of arbitrary size larger than 1. A language is a subset of sigma star, which is the set of all finite strings. And I'll use this absolute value notation to denote the length of a string. Then P is the class of languages such that there is an algorithm that correctly decides for all strings whether or not they are in the language, and runs in an amount of time that is polynomial in the length of the input. So this was introduced in the 60s as a notion of efficient computability. And one can argue about whether things that are in P are really efficient in practice or not, but But as a definition, it's a pretty good one, and so we'll stick with that and set aside sort of the philosophical issues of this quote here for another day. Okay, so let's try and make a polynomial time version of the axiom of choice. We can start with, this is the one we had originally. Let's just try and make everything in sight polynomial time. So instead of sets, they should be polynomial time sets, polynomial time languages. So we now say if S is a polynomial time collection of polynomial time sets, then there's a polynomial time choice function for S. Okay. This one, it's sort of clear what this should mean. This should mean languages in P, right? It's a set that's decidable in polynomial time. These other terms in orange, it maybe is a little less clear what these should mean, right? Like, what is our index set? How is our index set coded into strings, right? What is the input for this choice function and so on? So let's make some definitions here. All right, so this is just the definition I just had there. So let's say a polynomial time collection of languages is really one language. And what we're going to do is we're going to think of it as a language of pairs, x, y. And for a fixed x, you get this slice, the set of all y such that x, y is in our original language. And we'll think of this as one of the sets that's in our collection of sets. Okay, so when I say a polynomial time collection of languages, what I really mean is one language that's in P, where every slice in this sense is also in P. Okay, so this is nice because now our index for our sets are also strings. So now we can say what it means to have a choice function that's in P. If I have a polynomial time collection of sets, L, a choice function is a function f such that f of x is in the slice L sub x for all strings x, right? So our index set here, if you think about the index set in the usual axiom of choice, our index set is also sigma star. It's also the set of all strings. Okay. All right, great. So now we've at least defined all these terms. So great, we have some polynomial time version of the axiom of choice. And it was clear by construction, if you remove, poly time everywhere here, you get back the usual axiom of choice. Okay. But this particular axiom of polynomial time axiom of choice is a little unsatisfying because it's just false. So here is a polynomial time collection of sets with no polynomial time choice function. All right, and let me walk through this a little more slowly. So this is the same example. So at index x, there's only one string in that slice, which is you repeat x 2 to the x many times, exponentially many times. The reason there's no choice function here is just that if you have a polynomial time function and it gets x as input, it can't even write down this string because this string is exponentially long and it only has polynomial time. Okay, but this is sort of a silly reason to not have a choice function, right? So let's avoid that by definition. Okay, so we say a polynomial time collection of sets is honestly non-empty if for every x, the slice Lx has a string of length at most polynomial in the length of x. So this excludes this because the only string here has length exponential in x. Okay, and this notion of honesty is actually something that showed up a lot in Selman's work. I think maybe he was even the one to introduce it, not in this context, but in a slightly different context. But this issue of length, of things of exponential length, arises all the time when you're talking about polynomial time computation. And so you often need some assumption of honesty like this. Okay, so now let's modify this and have maybe a more interesting attempt at a polynomial time axiom of choice, which is if S is a polynomial time collection of honestly non-empty polynomial time sets, then there's a polynomial time choice function. Okay, this turns out to be equivalent to this statement, NP, MV, GT is C contained in FP. I don't actually want to define what all these terms here are, except to say that this was a complexity class introduced by Selman, and this was a problem whose study he initiated. And this containment implies P equals NP. So if, like most complexity theorists, you think P is different from NP, then you think also that this polynomial time axiom of choice should be false, right? But the point is it's somehow closely related now to P versus NP, right? A very classical question in complexity theory, right? I mean, the central question. Okay. All right, so let's see, questions about this, because now we're going to do several more examples of polynomial time axioms of choice here. We haven't said very much so far. We just have the definitions. So, okay. All right, great. Okay, so let's see another classical version of the axiom of choice, and its polynomial time version. So another version is, suppose you have a set of sets, Si, as before, but now they're pairwise disjoint. Then a version of the axiom of choice says there's a transversal for this set, which means there's a set T that contains exactly one element from each Si. Okay, so now with the definitions we had, we can make our polynomial time version. For every polynomial time collection of honestly non-empty languages, right? We still need this condition on the length that are pairwise disjoint. There's a P transversal for L. Okay, this one, I no longer know that it's equivalent to some well-known open problem or anything. It's, you can ask, how is this related to the other polynomial time version of the axiom of choice and other complexity questions? But there's a question here I want to highlight, which I think should be true, which is there such a collection, a polynomial time collection of honestly non-empty pairwise disjoint languages, such that every transversal is NP hard? Okay, if that were true, then that would say that if P is different from NP, then this must be false. Because for this collection, you would have to have an NP hard transversal, which is not in P, if P is different from NP. Okay, but I don't know the answer to this. All right. All right, so for the next couple versions of the axiom of choice, I now need to really introduce NP, because we're going to talk about it a bit more. So a language is in NP if you can verify that a string is in the language in polynomial time if you're given some additional witness. Okay, so formally, it's in NP if there's a polynomial time algorithm V, which we think of as a verifier, such that X is in your language if and only if there is a witness string W that is not more than polynomially longer than X, and V accepts the pair XW. Okay, so a classic example of this is three coloring. So the set of finite graphs G, where G is properly three colorable, right? You can assign colors to the vertices of G such that no two adjacent vertices have the same color. So this is in NP, and the idea is that W here would be a assigning of colors to the vertices, and V will accept on input GW if W is a proper three coloring of the graph G. Okay, and I mentioned this particular, I mean, hopefully many people have seen this before, but I mentioned this particular example because it's going to come up again in a few minutes. Okay. Right, and for those who haven't maybe seen it talked about this way, this is one way to formalize the notion of brute force search. So the idea is if something is in NP, you can decide whether or not X is in L by a brute force algorithm, which is enumerate all strings W of length at most polynomial in the length of X, and run your verifier on XW and see if it accepts. So the P versus NP question from this view is essentially, can brute force search always be replaced by an efficient algorithm? All right, and then I need one more variant of this for what I'm about to say, which is UP. So UP, I'm flipping back and forth here. UP is like NP, but this one additional condition, for every X, V, there's at most one W that V accepts. Okay, and the classic example of this is this language, which is related to factoring. So the set of pairs Ni, where the ith bit of the prime factorization of N is 1. Okay, so why is this in UP? Well, what does our verifier do? Our verifier will check that W is the prime factorization of N, say listed in increasing order or non-decreasing order, and then just checks, is the ith bit of that prime factorization 1? But the point here, so the U here is for unique. The point here is that there's only one W that V could possibly accept, which is the prime factorization of N. And then whether or not it accepts depends on what the ith bit is. Okay, so this class UP, prime factorization is, a classically hard problem, basis of a lot of cryptography. So UP, part of the interest in this class is precisely to talk about cryptography and cryptographic functions and how hard are they. Okay, so now we come to our third polynomial time version of the axiom of choice. So the classic version that we're going to use here says that every function has a one-sided inverse, which means for all functions f, there is a g such that for every x in the image of f of g of x is equal to x. So our polynomial time version is similar. We throw polynomial time everywhere, and we add this honesty condition. So what this honesty condition here is now saying, and this is the one that Selman really studied, is that f can't shrink too much. That if it has an input of length n, the output, for example, can't have length log n. It has to have at least length n to the 1 over c. And the reason you need this here is, suppose you didn't have that. Suppose f really shrank its input a lot. Well, then g, because g is polynomial time, it has no hope to get back to the pre-image, right? Because the pre-image could be exponentially longer than the image. So again, this honesty assumption here sort of avoids that sort of trivial length-based reason for something to be false. All right, this one, as phrased here, this is actually a thing that people had studied before. This exact question, as phrased here, they didn't say the axiom of choice, but exactly, honest polynomial time functions have polynomial time inverses. So Grohlman and Selman showed that this holds if and only if p is equal to UP. Okay. So this one now, we don't just have an implication with a classical complexity question like p versus np. We actually have an equivalence. It's exactly equivalent to this question of p versus UP. Okay. All right. Right, yes. And for those who spaced out for a minute, UP is like NP, but the witnesses have to be unique. There can be at most one witness. Okay. All right. And now the next one I want to present, the next version of polynomial time axiom of choice, it's actually going to be an NP version rather than a P version. Okay, but I bring it up because it has an interesting connection. Okay. So I want to come back to this problem of three coloring. So three coloring as a language, it's the set of finite graphs G where G is properly three colorable. It's NP complete. So it's in P if and only if P is equal to NP. But even though it's NP complete, so we think it's hard, there are lots of graphs where we know the answer. So for example, trees, the set of all trees are two colorable. This is, classic undergraduate combinatorics. And you can also decide if a graph is a tree in polynomial time, right? Is it connected and does it have n-1 edges? And not only that, but you can find a two coloring in polynomial time as well. In fact, a greedy algorithm works. Color one vertex black, color all its neighbors white, color all their neighbors black, and so on. As another example, same thing, graphs of maximum degree 2. Right? It's easy to test if a graph has maximum degree 2. So this is an infinite set in P. All graphs of maximum degree 2 are three colorable, and you can actually find the three coloring. Again, a greedy algorithm does it. You start coloring things. Whenever you come to a new vertex, it has at most two neighbors. Whatever their colors are, there's a third color available to you to use on that vertex. So here's the question. Is this always possible? If you have an infinite polynomial time subset of three coloring, can you actually find three colorings of those graphs? And this is what Fenner, Fortnow, Nake, and Rogers dubbed hypothesis Q. And in their paper, they showed this is equivalent to, I don't know, a dozen other statements. So what this says here is if you have a set of graphs that are all three colorable, and deciding whether a graph is in your set is in P, then there's a polynomial time function that will actually find a 3-coloring of those graphs. Okay, so this is a hypothesis. This is not a statement of fact. All right. So here, same thing, just shifted up. This hypothesis turns out to be equivalent not to a polynomial time axiom of choice, but to a sort of NP version of an axiom of choice, which is every NP collection of honestly non-empty languages has a polynomial time choice function. Okay. And so this, which is sort of a fairly natural, almost combinatorial question, right? If you have a poly-time decidable set of 3 colorable graphs, can you find 3 colorings in polynomial time? Is really equivalent to a version of the axiom of choice. Okay. And this, in their paper, they showed that, like I said, this is equivalent to, sort of a dozen other complexity statements that people have looked at with relations to all sorts of things. Okay, so what we start to see here is that somehow many things that people have looked at in complexity theory for a variety of reasons, right? Combinatorial optimization, cryptography, and so on, are all somehow closely related to polynomial time versions of the axiom of choice. Okay. And then the last thing I want to mention for this first half of the talk, focusing on AC, is there are lots of versions of the axiom of choice that are based on some statement about cardinals or bijections between sets. So Tarski's theorem, for every infinite set A, there's a bijection between A and A cross A. That's actually equivalent to the axiom of choice. So is the law of trichotomy, which says basically cardinals are totally ordered. So for every set, all sets A and B, either A is in bijection with a subset of B or vice versa. And too many statements to list based on cardinal arithmetic. So one example is for all infinite cardinals M and N, their product is equal to their sum as cardinals. Okay, this is equivalent to the axiom of choice. And if you look, there's a nice book by Ehrlich that I think it's called like the axiom of choice or axioms of choice, something like that. He lists, I don't know, like I said, 20 some odd different statements about cardinal arithmetic that are equivalent to the axiom of choice. Okay, which raises the question, suppose we want to make polynomial time versions of these. Well, we should be able to talk about polynomial time bijections and polynomial time cardinality, right? So what do we mean by this? Okay, and this will bring us to the second half of the talk, which is about polynomial time cardinality. So before I shift gears to that, any questions so far? Okay. All right. So this brings us to polynomial time cardinality. And this is now sort of more in the spirit of what you might call polynomial time model theory. For those of you who have seen computable model theory, we have a notion of cardinals and we want to talk about bijections, but we want everything to be in polynomial time. Right. Okay, and right, when I first came to this, when I was looking at the axiom of choice and I came to this cardinality stuff, I discovered this work of, for a long time, I was like, well, I don't know, that seems like a big can of worms, right? Like, do I really want to go down that road? And then I discovered there was a series of works by Nerode and Remmel where they actually worked out a version of polynomial time cardinality, very much in the spirit of polynomial time model theory, but for subsets of unary languages, meaning where the alphabet just has size 1. And part of the reason they did that was that a lot of the results from computable model theory, they could transfer to this polynomial time model theory over a unary language. In essence, because over a unary language, it's much easier to find the inverses of functions and things. There are only n strings, n unary strings of length less than n, whereas over a larger alphabet, there are 2 to the n strings of length less than or equal to n. And I found this very nice quote from Rod Downey in the Math Review's review of their paper, which says, it would be fascinating if the techniques of Nerode and Remmel could be used to prove that P equals NP is independent of intuitionistic ZF set theory via an analog of McCarty's work. Perhaps what is needed is the development of the theory over the standard languages, subsets of 0, 1 star. Okay, so I saw this quote and now I was like, oh, okay, all right, this seems kind of exciting. Like maybe I should actually put some time into developing this notion of polynomial time cardinality. And I should say, we don't get anywhere close to any of this, but we do this last little bit. We develop the theory of polynomial time cardinality over 0, 1 star. And to be frank, I'm not even sure I know what all of these words mean, at least as put together in this sentence. I know them independently from one another, but yeah, so if someone knows more about this, I'd be very happy to talk with them about it and see if we can sort of push in that direction. Okay, but for the remainder of the talk, we're just going to focus on the theory of polynomial time cardinality. Okay, so here's the definition. We have two languages. They can be over different alphabets, but we're always going to assume our alphabets have size at least 2. And we say they have the same P cardinality, or they are P equipollent, if there are partial polynomial time functions f and g, back and forth, f from a to b, g from b to a, that are inverses of one another when restricted to their domains. Okay, so the partial here and the when restricted to their domains means I have a polynomial time, say Turing machine, that computes f for inputs in A. Outside of A, that Turing machine can do whatever it wants. We have no restrictions on it. It could take more than polynomial time. It could not halt. It could be not injective. It could be not surjective. It could do anything it wants. Okay. So we're really, in this definition, we really are just focusing on inputs in the domain of these functions. Okay. And just some notation, I'll use this double bar sub P to be the P cardinality class of A. And we'll say that one P cardinal is less than or equal to another if A is P equipollent to a subset of B. Okay. So hopefully people recognize if you sort of drop polynomial time and so on from all of these, you get sort of the usual definitions of cardinality. Okay. So now we have this definition. Great. What can we say about this? Right. Well, it's a little funny compared to ordinary cardinality. So one thing is, it's no longer a total order. So the polynomial time law of trichotomy fails. So there exist pairs of incomparable P cardinals. Okay. And one way to do that is you build languages where you build sort of two languages where for long stretches, one of the languages has many strings and the other language has no strings, and then they reverse. And the idea is if those stretches are long enough, then a polynomial time machine sort of can't move between the stretches. And so you can't get a P equipollence in either direction because there aren't enough, you know, if this one is empty up here and this one has lots of strings down here, there aren't enough strings up here to map these two, right? And a polynomial time machine sort of can't move these strings far away from here because it only runs in polynomial time. Okay, so you can make that precise and that gives this result. Maybe even stranger, it's no longer even a partial order, it's just a quasi-order. So there exists sets A and B where A is P equipollent to a subset of B, B is P equipollent to a subset of A, but A and B are not P equipollent. So the polytime analog of Cantor-Schroeder-Bernstein fails, right? This says if you have two sets and each has an injection to the other, then there's a bijection between them. But with one more assumption, you can actually get it to work. So if we have polynomial time one-to-one functions from A to B and B to A with polytime inverses that are length increasing, meaning on every input, the output is longer than the input, then in fact, A and B have to be P equipollent. Okay, so this proof is actually similar to a proof of Berman and Hartmanis, who had sort of a polynomial time version of Cantor-Schroeder-Bernstein, but they didn't talk about P cardinalities. They were working in a slightly different setting. They didn't have partial functions, they had total functions. And a few other things, but the proof is otherwise very similar. The key thing here, for those of you who are familiar with Cantor, Shorter, Bernstein, that proof involves a sort of back and forth argument where you do sort of a P, Q inverse, and so on. This length increasing condition ensures that when you do that back and forth argument, you can't go back and forth more than a polynomial number of times. That's really why this is here. That's sort of what makes it work. Okay, so it looks a little different than ordinary cardinality, but we get sort of almost something that we would like. And that's to be expected, of course. It should look different than ordinary cardinality, right? I mean, it's not the same thing. Okay. What about the p cardinality of sigma star, right? Totally trivial language, all strings. In some sense, it should be like Aleph naught, right? But it's like the natural numbers. In another sense, it's not, in that all of our p cardinals are subsets of sigma star, right? All languages are subsets of sigma star. So in this setting, in fact, every p cardinal is less than or equal to the p cardinality of sigma star. So rather than being like a minimal infinite cardinal, the way Aleph naught is, in some sense, sigma star is like a maximal infinite p cardinal. Okay. And here you really start to see the difference, right? Because for p cardinals as sets, they're all countable, right? So of course it has to look different than ordinary cardinality. We never get beyond countable here, and yet you have distinct p cardinals among the countable sets. All right, so what can we say about this? Well, okay, maybe, what else can we say about cardinality? Well, one thing we have for ordinary cardinals is if you have two infinite sets and they differ only by finitely many elements, they have the same cardinality. Okay, is the same true for p cardinality? Well, for the p cardinality of sigma star, this is true. So let's call such languages p countable if they're finite or they have the same p cardinality as sigma star. If you have two languages that differ on only finitely many strings, then either they're both p countable or not. So the p cardinality class of sigma star doesn't change if you change your language by finitely many strings. Okay, that's nice, right? That's kind of like what happens for ordinary cardinals. But here we get something very different. So there exists an infinite language that is not p equipollent with any of its proper subsets. So if you've heard of Dedekind finite sets before, this is sort of Dedekind p finite, right? And this is very different than ordinary cardinals. Okay, and here this will be the one proof that I actually show you almost in full, just to give you a flavor. So the set we're going to use it's actually a unary set, but we're still, our alphabet overall is binary. So it's the set of strings of all ones where the length is of the form 2 to the 2 to the 2 to the k. Okay, why did we do that? Well, the idea is these strings are very far spaced out. And in fact, they're so far spaced out that if you have a string of length n in your set, the next smallest string has length n to the log n. Okay, and this is just some simple arithmetic with these exponents here. And this grows faster than any polynomial, right? Polynomials are like n to the c. This is n to the log n. Okay. So the idea is, suppose for contradiction that you had a p equivalence between L and a proper subset. What can we say? Well, for sufficient, imagine these are the strings of L. So they're getting further and further spaced out as you move to the right here. For sufficiently large strings, F can't move that string up because this string has length n to the log n, but F can be computed in n to the c time. So that means this string either stays where it is or moves down, which means that this whole finite set has to be sent into itself, but it's a finite set. So that really has to be a bijection from this finite set to itself. And then for much longer strings, well, they still can't go up because moving them to a longer string would be n to the log n. But now they can't go down either because we already have a bijection on all the smaller strings. So actually, F has to be the identity, and therefore L prime has to be equal to L. Right? Somehow the strings are far enough apart that F has no choice eventually of where to put them. And for the small ones, F could permute them, but that's all it can do because now it's working with a finite set. Okay. All right, so this, is quite different from ordinary cardinals. Another corollary to this proof is infinite p cardinals can have immediate predecessors that are only finitely different. So if you take that same language we looked at and you just remove one string from it, that turns out to be the immediate predecessor of this language, meaning there's no p cardinal strictly in between these two. That's actually not immediately obvious because you have these, like, yes, as sets, this one is a subset of this one, and it's just missing one string. So how could there be anything in between? But remember, we're allowed to use bijection. So like in principle, there could be a third set where this one is a bijection to a proper subset of the third, and the third has a bijection to a proper subset of this. But by a similar argument to this one, we can prove that can't happen. Okay. All right. Let's see. All right. So we're almost at our ability to use p cardinals to talk about axioms of choice. So the last bit we need is p cardinal arithmetic, which we define pretty much in the same way as ordinary cardinal arithmetic. So the product of two p cardinals represented by languages A and B is you take the Cartesian product of A and B, you encode that back into strings and you take the p cardinality. And the sum is you take the disjoint union. And the way we do that in computability theory or complexity theory is we take a tagged disjoint union. So the set of strings 0A where A is in A and 1B where B is in B. Okay. Now this, we start to get some interesting things. So, this gives it the structure of a semi-ring. So multiplication distributes over addition, the usual axioms for a semi-ring. And if you consider all the p cardinals that are in, say, P, there are only countably many of them because there are only countably many polynomial-time Turing machines. So in principle, this semi-ring could be finitely generated because it's now a countable semi-ring. My conjecture is that that's not the case. And I think proving this would be some interesting mix of complexity theory and algebra, which is why I conjectured it rather than just ask the question. Hopefully making it a conjecture spurs people on a little bit to try and prove or disprove it. But either way, I think it would be a very interesting mix of algebra and complexity. Okay, and then a very basic question about p cardinals is cancellation for multiplication by finite p cardinals. So if n is a finite set, is it the case that if n times a and n times b are p equivalent, then a and b must be p equivalent? And here, the reason I asked this particular question is Nerode and Remmel actually proved that in the unary setting, where the alphabet has size 1, this is false. There are counterexamples. But their proof, it really doesn't go through in the binary setting when you have strings over an alphabet of size greater than 1. And so I don't know, I don't have a strong feeling as to which way the answer to this should go. I would kind of believe either way. But it seems like a very basic question that we should be able to answer. Okay. And now finally, we come to polynomial-time axioms of choice based on cardinality. So here's one. For all infinite sets A and B, the product of their p cardinals is equal to the sum of their p cardinals. Okay. This, I have no idea what this corresponds to in terms of sort of ordinary statements about complexity theory. It seems like there should be something about, I don't know, polynomial-time Turing degrees and sums of Turing degrees and how they relate to unions and coupability and something, but I couldn't get a clean statement out of it. So this is sort of, there's a whole interesting class of polynomial-time axioms of choice here, where you can ask, do they correspond to more standard complexity statements, and are they equivalent to one another, right? If you look at some of the other polynomial time versions of the axiom of choice based on cardinality. Okay. Let's see. All right. So one last result I want to mention here, because it was sort of technically the hardest part of the paper, is a sort of density result. So if you have two sets A and B, and not only is A less than B, but it's much less than B. So it's not even P equivalent to any cofinite subset of B. So if A is P equivalent to a subset of B, then the difference between those two is infinite. Then there must be an infinite P cardinal strictly between A and B. Okay. As a consequence of this, there are no minimally infinite P cardinals. So for every infinite set B, there's an infinite set C where the P cardinality of C is strictly less than the P cardinality of B. Okay, so again, very different than the usual case. And the proof here, for those of you who have seen such things, it starts out in a way you might expect, which is there's some diagonalization, right? You're building a set in between A and B, diagonalizing against P equivalences. The thing that's very tricky is, at least when I tried to do that sort of in a straightforward manner, you run into what appears to be like an infinite injury argument, meaning you satisfy some condition, you've diagonalized against some string, later on you may break that. And then you have to come back and fix it, and you might have to do that infinitely often. And it was a huge pain. And eventually I realized there was a way to do it without injury. And the way to do it is to diagonalize against something slightly stronger than just saying there's no P equivalence from B to C and from C to A. And you have to kind of get that just right. You know, if you make it too strong, I don't know how to do it. If you make it too weak, it looks like some very ugly infinite injury argument. And eventually, after about a week of banging my head against the wall, I figured out sort of just the right thing to get it to go through with no injury, and sort of just the right strength of what I needed to diagonalize. Yeah, so I was very happy when I finally got that to work. Okay, but there's something funny here, which is, remember, this notion is only a quasi-order, right? So it's possible that C is strictly below B, meaning C is P equivalent to a subset of B, but C is not P equivalent to B. It's still possible that the converse could also be true, that B could be below C without them actually being P equivalent. So one question here is, okay, there are no minimal infinite P cardinals under this notion, but if you take the quotient partial order, do there exist minimally infinite P cardinals, right? So must any C in this corollary have this property that B is P equivalent to a subset of C? And from this construction, it's not obvious because this is some big diagonalization thing. Again, I don't know what way I expect this to go, which is why I phrase it as a question rather than a conjecture. Okay. So that was what I wanted to tell you today. There are lots more results in the paper, lots of things about other versions of the axiom of choice being related to previously studied complexity questions, some of the versions of the polynomial time axiom of choice being equivalent to one another, and so on. And as I mentioned at the beginning, lots of connections to the work of Selman that actually I didn't expect when I started writing this paper for the commemorative volume a year or two ago. And so it turns out that he actually did a lot of work on the polynomial time axioms of choice, kind of without knowing it. The big open question that I find kind of the most exciting direction for me is can we realize Downey's proposal here and show that P versus NP is independent of intuitionistic set theory somehow, using the model theory of P cardinals, right? And then there are lots of open questions around polynomial time axiom of choice and P cardinality. I mean, I mentioned a few in this talk, but there are, I think, probably a dozen or two in the paper about just things that for cardinals are sort of very basic, you can give as a homework exercise, but for p cardinals somehow become much more interesting. All right, so I think I will stop there, and I'm happy to talk with anyone about this and take questions. So thank you very much.